All right, welcome back. Today, we're diving into one of the coolest ideas in applied math, how systems of differential equations, which are just equations about rates of change, let us model the incredible, interconnected world all around us. And this isn't just about abstract symbols on a page. This is about taking reality and translating it into a language we can actually work with and understand. So, let's get right into it.
And this quote here really just hits the nail on the head. Coupled rates of change, that's the whole ballgame right there. It just means that things don't happen in a vacuum, right? The speed at which one thing changes depends on the state of something else, and vice versa. And this isn't some rare exception, this is pretty much the rule for how the world works.
I mean, just think about it for a second. A shift in interest rates totally affects consumer spending. The number of predators in an ecosystem is directly tied to the prey population. The flow of current in one little part of a circuit impacts another. So today, we're going to unpack the mathematical language that we use to describe these intricate dances of interaction.
All right, so let's get our hands dirty with our first case study. This one comes from the world of chemistry and fluid dynamics. It's a classic problem, but it's a classic for a reason, because it's perfect for really getting a feel for how these systems tick. We're talking about something as simple as mixing tanks.
Okay, so picture this in your head. You've got two tanks, A and B. Each one is holding 100 liters of water, and you've got pumps that are just constantly swapping water between them at a rate of 5 liters per minute. Now let's say we dissolve a bunch of salt into tank A. Well, that salt is going to start moving back and forth between the tanks, right? So the question is, how can we describe mathematically how the amount of salt in each tank changes over time?
At the heart of any differential equation is this core idea of a rate of change. So for tank A, its change in salt is just the rate of salt in minus the rate of salt out. Salt flows in from tank B and salt flows out to tank B. And that rate all depends on the concentration, the amount of salt divided by the total volume of water. And boom, here it is. This is what that whole process looks like in the language of math. Let's break it down really quick. That little x sub A thing, that just means the rate of change of salt in tank A. It's equal to the salt coming in, which is the flow rate, 5, times the concentration from tank B, minus the salt going out. And here's the kicker. This is the most important part. See how the equation for A needs to know what's happening in B, and the equation for B needs to know what's happening in A? They're linked. They're coupled. You can't solve for one without the other. And that, my friends, is a system of differential equations.
Okay, so that was tanks. Now let's take that exact same idea and see how it works in a completely different world. Biology. We're going from a physical system to a living, breathing ecosystem. How cool is that? So here's one of the most fundamental questions in ecology. Picture it. You've got a field full of rabbits, and you've got a population of foxes who, they love to eat rabbits. What happens to the fox population if the rabbit population suddenly booms? And then what happens to the rabbits when there are way more foxes around? Their destinies are completely tied together.
This classic dance is described by a really famous set of equations called the Lotka-Volterra model, and it's genius. It sets up two coupled equations. The growth rate of the rabbits depends negatively on the number of foxes. Makes sense, right? More foxes means fewer rabbits. But the growth rate of the foxes depends positively on the number of rabbits, because that's their food source. It's the same rate in, rate out logic, but for populations.
And what's so wild is what this simple model predicts. You'd think maybe they'd just find some stable balance, or one would wipe the other one out, right? Nope. Instead, they get locked into this perpetual cycle, an endless oscillation. More rabbits lead to more foxes, which in turn leads to fewer rabbits, and then, of course, fewer foxes. It's this beautiful and kind of brutal mathematical dance of life and death.
All right, for our last stop, let's jump into the world of engineering. We've done mixing fluids, we've done counting foxes, now we're going to chase electrons through wires. And you're about to see those same core ideas pop up one more time. If you have just one simple loop in a circuit, analyzing it is pretty straightforward. But that's not the real world, is it? Modern electronics are all about these complex networks of interconnected loops. And the current flowing through one part of the circuit absolutely influences the current in another part. They are, yep, you guessed it, coupled. So when you start applying the fundamental laws of electronics, things like Kirchhoff's laws, to these multi-loop circuits, you don't just get one tidy little equation. You naturally end up with a system of equations. They link the rates of change of the currents in each loop, sometimes even the charge on a capacitor. Again, you just can't analyze one loop in isolation. It's impossible.
Okay, let's just pause for a second. We've talked about salt in tanks, foxes in rabbits, and electricity in circuits.
I mean, these things seem totally unrelated, don't they? Let's zoom out and connect the dots.
This really puts it all into perspective. In chemistry, it was the amount of salt interacting between tanks. In biology, the predator and prey populations. In engineering, the currents in different loops. Do you see the pattern here? The specific details change, but the fundamental structure, this idea of an interconnected system, it's exactly the same.
And this right here is the big takeaway. This is what I really want you to get. Math provides this incredible, universal language for describing patterns. And this specific pattern of coupled rates of change is, well, it's everywhere. Once you learn how to solve these systems for one problem, you've basically unlocked a secret that lets you understand all of them. It's kind of a superpower.
So I want to leave you with this thought. Now that you know what to look for, you're going to start seeing this pattern all over the place. In economics with supply and demand, in medicine with how drugs move through our bodies, even in social dynamics. So the real question is, what other hidden systems of interaction are shaping the world all around you right now?